Hi, I'm Ethan Fish, and this is my CA7, the heat exchanger analysis. All right, we'll get right into the problem here. So this heat exchanger, water is used to cool hot engine oil with a mass flow rate of 8 kilograms per second from 100 degrees Celsius to 80 degrees Celsius. The water is entering the heat exchanger at 20 degrees Celsius with a mass flow rate of 2 kilograms per second. And this has an overall heat transfer coefficient of 1500 watts per meter squared Kelvin. Okay, this image here in the bottom right hand corner was kind of a rough drawing of the parallel heat exchanger that I chose to analyze. So you can see here water's coming in from the top here and traveling parallel with the oil, and then coming out exiting here, and then the oil is entering here, traveling along this pipe or tube, and then exiting on this side. That's why it's called parallels, because they're both flowing in the same direction. So I need to determine the exchanger type, which is parallel, heat transfer rate, effectiveness, and then all of the inlet and outlet temperatures, as well as determine the area. First, we need to start with a couple of assumptions. This is steady operating conditions for this system. Heat loss to the surrounding is negligible. The heat transfer from hot fluid is equal to the heat transfer of the cold fluid. So the overall heat transfer coefficient is constant and uniform, and the changes in kinetic energy and potential energy are negligible. Now we're getting into the calculations here. So we're solving for the heat transfer rate using this equation here of Q dot equals M dot oil times the CP of the oil, and then the del T of the oil across the pipe. So you can see here, we input the numbers. This number here we had to look up in the table in the back of the book at the specific temperature to get the specific heat. And then the mass flow rate was given in the problem. So we calculate that out and we get 355.2 kilowatts. And then we need to find the heat capacity rates of both the oil and the water. So as you can see here, they're both the same equations, just using different CP numbers. And obviously M dots are different between the two fluids. So you take the mass flow rate times the specific heat of the oil, and that comes up to 17.76 kilowatts, or 17,760 watts. Then you look down here, heat capacity of the water is same equation, just with different numbers. So 2 is kilograms per second is mass flow rate of the water. Then 4.18 is the specific heat of water. That gives us the 8.36 kilowatts, or 8,360 watts. Then, so our C min is equal to our C water, the heat capacity. Then we go down here, we do C min divided by C max, which gives us our 0.47. Now we're trying to calculate our effectiveness and our Q max. Our Q max is what we use to solve for the effectiveness. So Q max here, take our heat capacity rate, the minimum one, times the del T of the oil in and the water in. So we do that, 8.36 kilowatts times the del T gives us 668.8 kilowatts. So we go down here to find our effectiveness. We take our initial heat transfer rate divided by the maximum heat transfer rate, which gives us a 0.35 effectiveness, or 0.53, excuse me. Now we need to find the NTU value so we can find the area of the system. So our NTU equation is given on the top bullet point here, and solved out, it comes out to 0.88. So we take this 0.88 and our NTU value, plug it into our area equation here, which is NTU times the C min over U, so our heat transfer coefficient. And we plug those numbers in and we get an area of 4.904 meters squared. And then finally we are able to find the temperatures at all the inlets and outlets. So the T in and out for oil were given in the problem statement on the first slide. and as well as the T in of the water, which is good on the first slide as well. So we need to calculate the T out of the water. So with that, or to do that, we need to take the T in of the water plus Q dot over M dot times Cp of water. So we take our inlet temperature of the water, which is 20 degrees Celsius, over our heat transfer rate, our actual heat transfer rate, not the maximum, which is 355.2 kilowatts, divided by our mass flow rate of the water and our specific heat of the water, which gives us an exit temperature or outlet temperature of the water at 62.5 degrees Celsius. Thank you.